usually takes about a half an hour to maybe 45 minutes to actually do the lab itself. So why do we have 2 hours and 40, is it 2 hours and 40 minutes? 2 hours and 40 minutes for a lab that only takes 45 minutes. Because as I mentioned in class, we have time set aside in lab today for me to talk, partly, okay? But also for you to actually start working on the worksheet that's due for this lab. And if you do part of it at least during lab today, because you're gonna have time for that if you want to stay for it, then if you have questions, guess who can help you? Me. Right, and guess what's on the test next Thursday? This stuff. Okay, along with other things of course too. So this is a very nicely correlated lab with chapter 5. Okay, so today at the very end of class, we just got started on this topic that this lab is about today. We started talking about molecular equations, complete ionic equations, right? And non-ionic equations. We're going to be using that today as well. But we're also going to talk about something called exchange reactions. So most of the reactions we'll be doing today in lab are going to be exchange reactions. If you look at this, what I'm doing here, I have compound AX. So we're going to say, let's just say A is a cation, X is an anion, right? It would be an ionic compound. It also could be an acid or a base, by the way, because acids and bases also dissociate into cations and anions, right? So compound AX, compound BY, right? When it happens in exchange reactions, I recommend that everybody look up in the front here, okay? So I'd like to see people turn around looking, because if you don't follow this and understand this, when you get to the part of the lab and you get to the worksheet, you're going to be like, how do I do this? Okay? The hard part of the lab today is not actually doing the chemical reactions, it's doing writing the balanced molecular equations and non-ionic equations. Okay, so what I'm showing here is that compound, so cation A, basically, so you mix these two solutions together. I'm going to write here AQ, AQ, because we're going to start out with aqueous solutions of compound AX and compound BY. We're going to mix them, and then what they do is they dissociate into cations and anions, and then what happens is we get three kinds of reactions that can happen: precipitation, acid-base, or gas-forming reaction. But in all three cases, what happens is we write this out to figure out what's going on. We take cation A, go with anion B, as you can see, right? Cation B going with anion A. So they're basically switching partners. Would you agree with that sentence? Cations and anions switch partners? Yeah. Okay, so most of the reactions today are going to be this type, exchange reactions. Let me tell you the three types of exchange reactions. I already said it. One type is precipitation. Did I spell it right? Precipitation reactions. And in a precipitation reaction, guess what? One of these two products forms a precipitate, a solid compound. So for example, maybe this compound here is a solid, and it crashes out of solution. Maybe this compound here, even though I ran it together, is actually dissociated into cations and anions. So in a precipitation reaction, then one of my compounds I would form would have an S phase label, okay? The other type of reaction is called an acid-base reaction, also known as a neutralization reaction. So acid-base reactions are neutralization reactions. If I can write this correctly, it's like in here. Okay, there we go. And the third type are gas evolution or gas-forming reactions. Gas evolution reactions. I'll write the word reaction, reactions, acid-base reactions. And RX and S is a shorthand way to write reactions, right? Okay, so those are my three types of exchange reactions. We also are going to talk about another type of reaction today called redox reactions. I'm going to wait to talk about those till later, because I don't want to sit and talk at you for a super long time, okay? So I'm going to split my talking today into two types. Right now in the beginning, and then later on in the middle of the lab as well, when everyone's got their actual experimental part of the lab done today. Now, I want you to get your lab out. If you don't have it printed out, I want you to go to the computer, open up the lab itself, because I'm going to actually go through two examples from the first page and the second page of this lab, okay? So you'll know what I'm going to be talking about here. So the first thing I'm going to talk about is, even though I just wrote on my list precipitation reactions, acid-base, and then gas evolution, I'm going to talk first about acid-base reactions. So as the name implies, for an acid-base reaction, you have to have an acid and a base. How do we recognize an acid from a formula? Remember this from when we talked about it earlier, before the last test? One or more H's in the front part of the formula, right? So this one, of course, is hydrochloric acid. And the hydrogen chloride is dissolved in water. It's called hydrochloric acid, so that's why I know it's an acid. And my base in this case is going to be sodium hydroxide. So most bases have OH as their anion, but not all. So right now we're going to just focus on that type. Okay, so that's my base. I'm going to write AQ here. Now, even though the first page actually has those products written out, I want to go through a process to figure out the products A, Y, and BX like this. Okay? And this process is the process you'll be using for all three types of exchange reactions, whether you're doing precipitation, acid-base, or gas-forming reactions. What I do is I look at the formula and say, okay, if this is actually in the water, it's going to be dissociated into cations and anions, right? So I write those out. I'm going to write H plus, Cl minus. Do you guys agree with that? From that formula? And I'm doing this so I can write the correct formula for my products. This is my overall general reaction. It can get more complicated than this, just so you know. So it's my H plus Cl minus, right? And my sodium hydroxide, when it dissociates, is Na plus OH minus. So far, so good? So I'm writing out those symbols and charges of my cations and anions to make it easier for me to write the correct formula for my products. This one's actually a fairly easy one. So I started out with the easy one. So I'm going to basically, following my pattern here, this is my A, right? So this cation goes with this anion. Would you agree with that? From the pattern over here to the right, to your left, or my left, your left as well. So that goes with that. And then this one goes with this one. So let's just start out with the H plus and the OH. What happens when H plus and OH basically come together and react? Anyone have an idea of what might form in that case? Water. H2O. Right? So plus cancels out with the minus, we get H2O. So one of my products, I'm just going to go in the order here. What do I have? Put my water over here on the right hand side because I'm just following the pattern on my first page of the lab. Although the water could go here as well. And I put an L for a phase label. So whenever you form water in any reaction today, you will have L for your phase label. And that is the only time you're going to have a phase label of L. These ones I have AQ because HCl is an aqueous solution. Sodium hydroxide, it is an aqueous solution of that. That's why I have those AQ phase labels. And by the way, for all the reactions today, the phase labels are very important. So that's my first product, or one of my products. What's my other product? Can anyone tell me the formula of my other product that formed here? NaCl. So even though the chloride is written first and the Na is written second here, I have to switch that. Because when you write an ionic compound formula, you always write the cation first and then the anion, right? Okay, so those are my two products. Well, the liquid, there's not a lot of heat given off of this. There's some heat, but it's not enough to turn this all into a gas. That's why the water's liquid. But this sodium chloride here, you already know sodium chloride dissolves in water, right? It's soluble. So we're going to write an AQ. But let's say we made an ionic compound in this acid-base reaction that we didn't know if it was soluble or not. Let's say it was something we didn't know off the top of our head. We all have experience with sodium chloride at home, right? What you're going to do is you're going to get the solubility rules, which I will get them from my office and pass them out. But if you go into the, I'm going to show this on the screen really quick here. Just a second. I'm going to find it in my notes. It's also in the book, but I just try easier to find the book in the notes. There they are. Okay. Now, you know what? I'm going to just, I'll talk about this in just a minute. I'm not going to put it on the screen right now. So in your notes on page 5.8, also in your textbook, I will pass out a little sheet that you'll have in the test next week. There is some solubility rules that we're going to be using. So, oh, actually, maybe I should show this right now. I take that back. Let me turn this on. Okay. So the solubility rules are in your textbook. I have little half sheets of paper like this that I'm going to pass out next Thursday on the test. I will get those from my office and give them to you to the lab today as well. So you have those handy, because you don't have to memorize this. Isn't that lucky? Okay. Oh, sorry, lucky. I know that memorization is a pain. There's a lot of information here. I'm going to show you how to use it. Okay, so we're trying to figure out the phase label if we didn't know sodium chloride was soluble. We know it's soluble, so we know it's going to dissociate into cations and anions in water, right? That's why I wrote the AQ, because AQ means aqueous solution where everything is dissolved, right? And ionized in the case of ionic compounds. So the solubility rules tell you this. So this top part is it's separated into two portions. The top part says compounds containing the following ions are generally soluble. Okay, and you'll see this first line, lithium, sodium, potassium, and ammonium cations. They're soluble always, no exceptions. So anytime you have a compound that has any of those 4 cations in the formula, like you could have sodium chloride, sodium sulfate, sodium phosphate, whatever. Anytime you have Na plus in a formula, it's going to be soluble. And the phase label you use for the compound formed when it's soluble is what? AQ, okay? What does S stand for again?
Solid.
Solid. So anything with those 4 cations, let me zoom this in a little bit, are always soluble. The next line down, it says nitrate and acetate. How do I know the names of those? Because I've memorized it, that's why. So when we did this stuff, when we covered this stuff for ionic compound nomenclature in the last test, it's mentioned, I think, once or twice that it's going to follow us. It's following us today, and next Tuesday, and the test next Thursday, okay? So if you don't know those polyatomic ions, you need to learn them. So whenever I have a compound that has nitrate or acetate in it, it's also always soluble, right? No exceptions. So even though I said you don't have to memorize the solubility rules, what I'm going to tell you is this. If you memorize those first 2 lines, that can make your life easier, not harder. Because then if you see a product and you say, oh, it contains any of those things, I know for sure it's going to be soluble, and I'll put an AQ phase label. So once you go down to the rest of these, you'll see that, for example, chloride, bromide, and iodide are normally soluble, but there's some exceptions depending on what cations they're with, right? This one here also, normally soluble, but there's some exceptions if certain cations are paired with that anion. So that's the top part of the solubility rules. So based upon the fact that sodium, no matter what anion it's with, is always soluble, do you see why I'm going to put an AQ phase label even without my home knowledge that sodium chloride is soluble? Right? Down at the bottom, this part of the table says the compounds containing the following ions are generally insoluble, with the exceptions listed over here. So if I have a compound with hydroxide in it, and if there's any of these other cations, lithium, sodium, potassium, or ammonium, then it's going to be soluble. By the way, didn't we just talk about the fact that these are always soluble? So there's my only exception for hydroxides right there. So if I learn that first line and that second line, I've just learned that line right there as well, right? But you're going to have this table both today and on the test next week. Okay, so now with that, let me shut this down so I have to go back to the screen. With the solubility table, it's handy. I can look it up and I can find out that NaCl is a soluble ionic compound, which is why I write my AQ phase label, not from knowing this from home. Okay? From the solubility rules. So I've written my correct product formulas. I've written my correct phase labels. Is this equation balanced?
Yes.
Yes, it is. So basically, what I have just written is called the balanced molecular equation. I'm going to call it the BME, okay? So when I write BME, that means balanced molecular equation. So in class today at the very end, I talk about writing molecular equations, but I'm going to add the extra word balanced in there because it has to be balanced. Correct formulas for reactions and products, correct phase labels, correct stoichiometric coefficients, right? Okay, so that's my balanced molecular equation for that acid-base reaction. Now what I'm going to do is I'm going to write the net ionic equation for this reaction. And to do that, I'm going to first write the complete ionic equation and then cancel spectator ions, like we did in that one example at the end of class today. So to do that, what you do is you look at your formula, your phase label, and decide whether you should associate out your cations or anions or not, right? So in this case, should I separate it out? Well, if you see an AQ phase label like that, and the acid is a strong one, you will then dissociate it out. So anytime you see, let me just write this 1 second. Here is the general rule for when you're going to split apart your compounds into cations and anions. First of all, you have to have an AQ, okay? So if you see an AQ, that means it's very likely, not for sure, that that compound can be dissociated into cations and anions. And when I say very likely, is because there's 2 main types of compounds we have to deal with. There's ionic compounds, and if it's an ionic compound with an AQ, that means it's a normal cation, anion, not an acid, not a base, okay? You see AQ, it means dissociate into cations and anions for a complete ionic equation. If it's an acid, however, you got to be careful. So this is an acid, right? It has AQ. If it's a strong acid, which I have to memorize for the test next Thursday, then A, dissociate 100% because strong acids are strong electrolytes. They 100% dissociate, right? If it's a weak acid, however, then I wouldn't dissociate it. And we'll do another example about this later. Because I know this is a strong acid, that's why I separate this out into H plus Cl minus, okay? Sodium hydroxide, that's one of the strong bases, so I'm going to do the same thing. Na plus, OH minus. So you basically separate out into what they really are in solution. What about my sodium chloride? Should I split that apart into cations and anions, or should I leave it together? I hear split it apart. Why? It's just your normal ionic compound with an AQ. It's not an acid. I have to worry about the acids are the ones I have to be careful with because they have weak acids and strong acids. If I have an ionic compound with an AQ, split it apart. Okay? We're going to go Na AQ plus Cl AQ. And now I have my water I have to deal with. Is my water molecule actually separated out into H plus and OH minus once that water has been formed?
No.
My acid-base reaction? No. It's basically almost 100% together as water molecules. I say almost 100% because there is a small percentage that is dissociated apart. But it's so tiny, we just ignore it. So my water is going to stay together. So here's the shorthand way to do this. If you have an L, G, or S phase label, that compound stays together. Okay? And by the way, water is a molecular compound, not an ionic compound. It does not dissociate into cations and anions. That's another evidence that this is not going to come apart into cations and anions. Yes?
Do aqueous solutions usually come apart then?
If it's a normal ionic compound, not an acid, they all come apart. Okay? They're all strong electrolytes. The acids are the ones you have to be careful for. For acids, you have to look, is it a strong acid or a weak acid? How do I know that? I look it up or I memorize it. For today, you can look it up. For next Thursday, you have to have it memorized, right? So this is one of the acids on the list. It's a strong acid, and then I dissociate. So that's the only one you have to be careful with an AQ are the acids. For any ionic compound, if you see an AQ, strong electrolyte, 100% dissociation. Because those all 100% dissociate, yes.
So if it's a weak acid, it doesn't disassociate?
Then we keep it together. And I'll do an example of that later.
Okay.
So right now I'm going to do the strong one. I want to just bring that up right away though, so you realize you can't always go only by AQ. The acids you have to be careful with. But the normal ionic compounds, which means any other type of ionic compound that just contains your metal cation, non-metal polyatomic anion, or ammonium, you can just separate those out. Okay? Just acids are the ones to be careful with. Okay, so now we're going to deal with our spectator ions. What are our spectator ions here? Well, the sodium is the only thing that's exactly the same on both sides, right? Like the example we did in class today. Well, this is obviously a different example. Well, actually, I'm wrong. There's two things. I wasn't looking carefully. The chloride's the same as well. Right? The H plus and the OH came together and formed a covalent bond to form water molecules, so that's where my chemical reaction happened. So what we're trying to show then in a net ionic equation is we actually want to show the reader of that reaction what actually happened. Well, what actually happened is this. The H plus from the acid reacted with the OH minus from the base to produce water. So you cancel out your spectator ions and you make your net ionic equation, which I'm going to call NIE from now on. Okay? So far so good? If this has been balanced and you did everything right here, this should be balanced as well. Okay? You shouldn't have to rebalance this if you balanced up here already. Any questions on this example? Where's the lab go? Move the lab to next here. Like I lost the lab. Okay. Oh, here it is. I found it again. Any questions one more time? I have one more example to do before you start. Yes?
I thought OHs are inside.
So the hydroxides are when they're with, that's a good question actually. So that's when hydroxides are with, like for example, in a ionic compound. So that solubility rule table is for ionic compounds, not for acids and bases, okay? So you'll look on that solubility rule table, you're not gonna find any water around there, you know what I mean? Because this is the hydroxide reacting with H plus to form water, which is not an ionic compound, it's a molecular compound. So yeah, very, very good insight. So for example, instead, let's just say I had this instead. Let's say I had just pretend that one of the products I would make would be calcium hydroxide right here, okay? If you look at the solubility rules, well, I think I might have just picked one that's also, oh, I picked another soluble one. Let me pick another one. The solubility rule says that one's also soluble, by the way, it's an exception. So let me pick one that's not. I'll do magnesium. Let's say I had this one here. So hydroxide is my anion, here's my cation for an ionic compound, right? Specifically a base. So that deals with ionic compounds, acid bases, and normal ionic compounds, not molecular compounds like water. Okay, make sense? Okay, any other questions about this first example before I go on into other examples? One more example. Okay. This next example is also right off the front page of the lab. Now this one is a different type of reaction, but it's the same similar pattern of what we're going to do. Okay. So what we're doing is we're taking an aqueous solution of lead 2 nitrate and an aqueous solution of sodium sulfate. And before I even talk about this, notice that I have a nitrate here as my anion, right? Remember that second line in the solubility rule said that nitrate and acetate, no matter what cation they're with, they're always soluble, right? See that AQ there? That means that that's a soluble ionic compound. It means it associates into cations and anions. It dissolves readily in water. That's what that means, right? What about that sodium right there? Anything with a sodium, potassium, lithium, ammonium cation, no matter what it's with for anion, you're going to also have a soluble ionic compound, which is why I have AQ there. So I take 2 clear solutions of those 2 compounds and I mix them together, dump them together. We're going to figure out what the products are. Well, how do we do that? We're going to do an exchange process. But in our exchange process, the best way to do this, to not make mistakes, is to figure out your charges of your cations and anions like we did here, even in the net ionic equation part, okay? So what's my charge and symbol for that? Well, we know the symbol is Pb. What's my charge on that lead cation in that compound? Pb what? 2. Plus 2, you are correct. How do we figure that out? Well, the shorthand way is that 2 comes up here and the 1 goes there, right? Remember that crisscross stuff we did for nomenclature? So the lead is plus 2. In fact, this is lead 2 nitrate. What's the formula? Well, the formula of nitrate, we already can see it there. It's NO3. What's the charge of the nitrate? -1, because I memorized it or I figured it out for the formula, right? Now right now, we're not going to put the 2 in front of here right now like we would have to do for the complete ionic. We're going to just figure out what is the symbol and charge of our cation and anion to help us figure out the correct formula of our product. This is the hardest part of these types of reactions. So far, so good? There's a reason I'm doing this versus just saying, this goes with this and this goes with this, okay? In fact, well, let me keep on going here. What's the charge on the sodium cation?
Plus 1.
Sulfate's applied to my ion. What's the charge on the sodium cation? I hear plus 1. I'm going to remind you how to do that. So sulfate's a polyatomic ion, right? So you just have one of those. So the sulfate's -2, the sodium's +1. You can also look on the table and find out if it's in column 1A or group 1A, right? Make sense? It's important that you can figure out those charges. If you can't do that, which follows us from the ionic compound nomenclature stuff, it's going to make it hard to write the correct formulas. What's my charge on a sulfate? I just got done telling you.
2 negative.
Okay, -2, right? Okay, there's a reason I'm doing this. You're going to find out right now why it is. If I had just said, oh, I'm going to follow my AXBY pattern here, I'm going to do this. I'm going to go PB goes with SO4, and Na2 goes with NO3, 2. So far, so good? See what I did there? I just did my switching. Sometimes you get the right formula for your product, sometimes you do not. This is a case where one of the products has the right formula, but one does not. Let me show you why that happens. So here we have our PB +2 and our SO4 -2, right? So this cation goes with this anion. So then I, on my little arrow, say those 2 go together. So it's +2 -2. So 1-to-1 ratio is right here, isn't it? So far, so good? Yes.
Why is your Na only like +1, but you have 2?
Okay, so right now I'm not dealing with how many I have. All I'm dealing with is what is the symbol and charge to try to figure out the formulas. That's a good question. So for when I do the complete ionic equation, then I have to write out the 2, okay? But for now, I don't care about how many I have, I just care about what the charge and symbol is on each cation and each anion. Okay, so later on I'm gonna worry about that, but that's a good question too. You have very good questions today, by the way. Okay, okay, so far so good. This one does match up with that? So that is correct. So that first one is correct based upon the charges of my cation and anion. If I have Na going with NO3, Na plus NO3 minus, what's the formula for that? NaNO3. It's 1-to-1, isn't it? Plus 1 minus 1. Would you agree with that? Is that the right formula for sodium nitrate? No, it's not. This is why we need to write out the symbol and charges of everything to figure out the right formulas, because we have to use that knowledge we already have from the ionic compound formula chapter to write the correct formulas. So this is not correct. What is correct is NaNO3. So our first and hardest thing we have to do, honestly, in all these exchange reaction products, to write these products, is to write the correct formulas. So figure out the symbol and charge of your cation and anion. Don't worry about the numbers yet, just worry about what is the symbol, what is the charge, what is the symbol, what is the charge, right? Do your little exchange. Look at your charges and make sure you write the correct ratios of your cations and anions. And now we're going to do the balancing and phase labels. So let's just balance first, okay? Is this equation balanced right now? No, because I just changed the formula. Before it was with the incorrect formula. That was not a correct equation, because the formula was wrong, right? I have 2 sodiums here, only 1 over there. I'm going to put a 2 in front of this one, and now I have 2 nitrates, 2 nitrates. Is this equation balanced? Yes, it is. So you balance it after you write the correct formulas. Okay, what else do I have to do to finish this balanced molecular equation? Look at the one right behind me over here for the acid-base reaction. What is missing over here?
Labels.
The phase labels. So you have to have phase labels for everything in your balanced molecular equation and your net ionic equation, okay? This complete ionic equation, that's just, we do this along the way to get here, okay? This is our work to get to this point. We're not to that point yet anyhow. So now we're going to, so our phase label, well, let me do this. I will just tell you, I'm not going to put the screen back on. So I go to the solubility rules and I look up, so lead's not on here, but sulfate is on here. So I look at the solubility rules. Sulfate's in the top portion, but it says, on the right-hand side, it says, when sulfate pairs with lead plus 2, the resulting compound is insoluble. So based upon me looking at this table, what should I write for my phase label for my lead 2 sulfate? S. When it's insoluble, that means you're going to form a precipitate, a solid. It's going to come out of solution. And you're going to see cloudiness. What about this one here? NaNO3. S or AQ? How do I know it's going to be AQ?
Sodium.
Sodium, lithium, potassium, ammonium, always soluble, and nitrate acetate, always soluble, right? So if I memorize that, I don't have to even use the solubility table, right? But if I didn't, I just go look it up. That is my balanced molecular equation for this reaction. Now we have one more thing we have to do here, and I'm going to get started. We're going to go through now and again write a net ionic equation. What's the time? Okay, we're about where I thought we'd be. So to write the net ionic equation, you have to first go through the complete ionic equation, especially when you're first starting this out. After a while, when you get the hang of it, you may not have to do it. The lead 2 nitrate AQ, what should I do? Keep it together or separate it apart into cations and anions? Yes, this is not an acid, is it? So if it's just a normal ionic compound, which this is, with an AQ, it means dissociates, a strong electrolyte. So now I'm going to do this, Pb plus 2, and I write 2NO3, because now what I'm doing is I'm writing out an equation that actually shows what's actually happening with this solution. For every one of these compounds together, I get 1 lead plus 2 and 2 nitrates. So now I'm dealing with that coefficient of 2 in front of here, okay? In the process of writing the complete ionic equation to get the net ionic equation. What about that sodium sulfate? What should I do with that? Separate, or I hear separate. Anyone want to say together? No, it's an AQ and it's not an acid. Separate. So now I write 2Na plus because of course the formula says Na2, right? So I put the 2 out in front for the 2 sodiums. and I have one sulfate. Now, and these are of course AQ as well. What about my lead 2 sulfate? Apart or together?
Together.
Why is it together?
Salt.
Because I have an S. S, G, and L phase labels stay together, always. S, G, L stay together, because in solution, these are not separated, they are together, which is why we have the precipitate. And this, by the way, is a precipitation reaction. That solid that forms is a precipitate. What about my sodium nitrate? Apart, because it's an AQ and it's just a normal ionic equation or ionic compound. It's not an acid. The acids are the ones you have to be careful with. You have to identify whether it's a strong acid or a weak acid. So we get 2 Na and 2 nitrates. So it's kind of messy here, sorry, but it's kind of down there. What do we do next? After we write all of our things for our complete ionic equation to get our net ionic equation. We cancel our spectator ions just like we did in this one, just like we did in the one in class today, and after a while it gets to be old hat, right? After you get enough practice with it, and if you stay today, you will get enough practice that this is going to get easy hopefully. So my spectator ions are the ones that are exactly the same on both sides, right? And they're called spectator ions because they are just spectating at the reaction that's actually happening. If there are little people in there looking, they're just watching things happen. They're not doing anything. They're floating around the beginning, floating around at the end. That's why they're called spectators, because the real stuff that's going on is the lead plus 2 is reacting with the sulfate minus 2 to form our lead 2 sulfate solid. What do I call that again? I call that the net ionic equation. So this is my NIE. Okay, so every reaction you're going to do today, which includes numerous precipitation reactions, 2 acid-base reactions, and a couple gas evolution reactions. I have not talked about these yet. I will talk about them in the second part of my little talk today. Okay? Every single one of those, that you see something happen, you have to write out a balanced molecular equation with all your phase labels for everything and a net ionic equation. The lab tells you this as well. I'm just saying it out loud. Okay? When you get to the redox reactions, I'll talk about those later as well. Those ones we have some extra things you have to do as well. But even the redox reactions that we'll be doing at the end of all the reactions today, you'll also have to write out a balanced molecular equation and a net ionic equation. I'm going to write down here really quick, redox equals reduction, oxidation. So the last type of reaction we'll be doing today, and I'll talk about it later in more detail, are called oxidation reduction or reduction oxidation to go along with my short version of it called redox reactions. We will start talking about this next Tuesday in class. Will redox be on the test next Thursday?
No.
No, that's the last section of chapter 9, or not chapter 9, chapter 5, the section 5.9 that will not be on the test. Does that mean you don't have to do that part of the lab report for this, the worksheet that's due next Thursday? You still have to do it. You have your book, you have resources. You still have to finish that last part, even though it's not on the test, okay? But the majority of this lab today is actually about this, anyhow. Okay, any questions? Okay, I'll let you get started.